Okay, so the next topic that we're going to talk about is minimum spanning trees. And minimum spanning trees are something you should be familiar with. They're covered quite a bit earlier in the curriculum. It's typically one of the earlier graph algorithms that you see. So a lot of this I'm hoping will be review. But I wanted to go through things, and then at the very end, I'll talk about a few slightly different applications or some, slightly different ways to think about minimum spanning trees that might help you when you see problems that involve them. So, couple of quick reviews first. Well, first of all, this is our second topic focused on undirected graphs. The earlier one was bridges and articulation points. So if you have not already looked into the bridges and articulation points, if you missed it in class, please go back and review that material also. Okay, so the idea of or I guess for another review topic, I want to just remind you that the definition of a tree is something that is going to be n nodes connected, fully connected with n minus one edges. Okay, so if you have n nodes fully connected with n minus one edges, that is going to form a tree. So the way that you probably learned about trees to begin with a particular root and children off of the root and so on, is one way to think about trees, but you're not required to actually have a root. So you can have something that's a tree without the root being defined. You can, pick any node to then be the root and kind of change that. And so this is going to matter for graphs because when you have a graph, the the different nodes that you have, uh, you know, can form a tree structure, even if the thing that you look at doesn't necessarily look like it ought to be a tree. So, for instance, this is a tree there, and that's not, you don't obviously look at it. You can't necessarily pick out what node is the root node or anything like that. But that meets the definition of a tree. And there's other aspects like there's only one path between any pair of nodes. That's another way you can describe a tree and so on. Okay, so there are two algorithms out there for handling minimum spanning trees. And I will admit I always get the names mixed. I can remember the names, but I can't remember which one is which. Uh, but I review it before I talk about it, so I remember right now. But don't feel bad if you can't remember which one is which, but you should remember these two different types. Neither one is a very complicated algorithm, but they're Kruskal's and Prim's algorithms. Um, Generally, there's tiny reasons that you might want to favor one over the other. It typically has to do with the way your data is coming in and what you want to handle, or just do you feel more comfortable handling priority queues or union find? Either one of those are there. So basically, both of these are going to run in order E log V time in the end. So you have to visit every edge, and then you'll do a little bit on top of that from there. But you can come up with specific scenarios where one or the other might be better. So let's go ahead and start with Kruskal's algorithm. So Kruskal's algorithm is going to be based on a union find structure. Okay, and it will assume that you have an edge list. So in other words, you just have a big list of edges. Um, I guess I should define what a minimum spanning tree is first, but an edge list with weights. And as a reminder, what a minimum spanning tree is, I should have mentioned this before, is if I'm given some graph, well, let's make this graph much more complicated, uh, something that is no longer a tree. Okay, if I'm given some graph and every single edge of this has some weight associated with it. Okay, so there's a bunch of weights. You want to find what is the tree that connects all of these nodes. So something that's going to connect them. So we're going to have, if there's n nodes, n minus one edges, and we want to do so with the minimum weight. So this problem goes back, I think probably some of the earliest applications of it were things like you want to set up a network of some sort and you want to find the cheapest way to connect everything in the network. And so if there's a cost between setting up a link between any two nodes, find the cheapest way to do that. And you can imagine, say with a telephone company or something back in the olden days, then the cost to run a phone line over various terrain might make it much easier to connect one city to another. Uh, versus a different pair. So anyway, that's the basic idea is the minimum spanning tree. So with Kruskal's algorithm, we're going to assume that we have an edge list with weights, and we will sort the list from lowest to highest. Okay, so we're going to basically, and this is kind of obvious, you want the things that have the lowest weight. So we'll just go ahead and sort our entire edge list with the weights. Now, notice that's going to be like an E log E algorithm right there. So, I talked about the running time before, just realize that, depending on the size of E versus V and so on, these things can, you know, that running time is maybe not the way you would want to think about it overall. Okay, so anyway, sort the list lowest to highest weight, and then you're basically going to repeat the process. You take the next edge and check if the two nodes are in the same set. Okay, so I mentioned before that this is based on union find. So union find is going to start out with each node in its own set, and we're going to gradually join them together until everything is connected. So if they are in the same set, then we will ignore it. If not in the same set, add this edge to the MST and union the nodes. Okay, so I'm going to give you a quick example because I think it's pretty easy to see this. So I'll draw a pretty basic graph here, just something simple to let us review the process. Put edges kind of in a nice pattern. And then I'll pick different edge weights here so that we can see them. And I'm going to pick unique edge weights so that it makes the problem easier to see. Realize that the edges don't have to be unique. There could be more than one minimum spanning tree. There's not necessarily a unique one when you have edges of different weights. Okay, so there's a graph, edges numbered 1 to 11. Those are the weights on those edges. And we want to connect these 6 nodes. So we're going to pick 5 edges to do this. So you have these nodes, and maybe I'll note these just to be easier. A, B, C, D, E, F. Okay, so we have A through F. We will go ahead and at first, A through F are all in their own sets. So A, B, C, D, E, and F. And I'm going to put them in the same column when I union them together in the end. And so we go through and we check our edges in sorted order from the smallest, the minimum edge, to the highest. So the minimum edge is going to be the very first one, which is number 1. It has weight 1 in this simple example. So that's this one right here. Okay, and notice that it is connecting B and E. Okay, so 1 is going to connect B and E. And so we check and we say, are B and E, are they in the same set? No, B and E are in different sets. So we will go ahead and keep this edge. I'll mark it in green here. We'll keep that edge and we will union B and E together. So I'll put E in the same set as B. And so remember our good friend, the union find algorithm, lets us merge sets together or check what sets are together. So next we go to the next highest edge. In this case, since I numbered the edges 1 to 11, the next highest one is 2. So that's this one over here. So 2 would connect C to F. Okay, so we check again. We say, are C and F, are they in the same sets? No, they are not. So we go ahead and we keep that edge. Okay, so we kept 1, we kept 2, and we go ahead and we merge C and F. So we'll have F here. Okay, so now we have just 4 sets. Now we go on to the third one. We look at node 3. So 3 is going to connect D and E. So over here, we will look at D and E, and those are not in the same set. So again, we keep node 3. That's one that we will keep, and we will merge those two together. So D gets added to the same set as E is in. Okay, I'm not showing the union find structure. You hopefully remember how to do that. Okay, next we go on to number 4. So we look at 4. So 4 is going to connect D and B. So we look and we say, oh, D and B are already in the same set, so we do not want to use this one. This one is not going to get used. So not an edge that we are going to add to the minimum spanning tree because it would be connecting things that are already in the same connected component. It would be creating a cycle. There would no longer be a tree. Not something that we want. Going forward, we take node 5. So 5 will connect B and C. And so over here, we look and we say, here's the set for B and here's the set for C. Those are different, so we're going to keep edge 5. That becomes part of our MST. And we will, again, merge these two groups together. So C and F go over here. All right, and we're almost done. Go through here, find edge 6. 6 is going to connect E and C. And so when we check over here, E and C are in the same group, so we do not want that. That is not an edge that we want. Not going to use 6 as part of our MST. And then finally, this should be the one that fixes it for us. 7, so edge 7 connects A and E. And so if we look over here, A and E are in different sets. So we go ahead and we add that to our minimum spanning tree here. And that edge becomes part of it. And again, we merge these together. So in the end, everything is in the same set. Everything's been unioned into a single set at this point. If we had kept going through edges, we would find that we wouldn't need any more. You can stop as soon as you connect everything. So as soon as you get everything down to a single set, once you have n-1 edges added in, you're done. And that's Kruskal's algorithm. Okay, so pretty simple algorithm, should be easy to implement, especially if you already have your union find. Again, we've been using union find a lot in the course, so and you'll see it more. This is yet another example of it. Okay, so next one is going back to the other algorithm, is Prim's algorithm. And so this one is going to be based on a priority queue. Okay, and that's supposed to be QUE. So priority queue. So Prim's algorithm is going to sort of build things out instead of sort of creating the term for what you have here is an arboration, I believe, where you have multiple trees and eventually they converge into one tree, but it starts out as a bunch of separate trees that gradually merge together. And eventually you end up with one tree. So instead of having an arboration, Prim's algorithm is going to use a priority queue and it's going to build out from some vertex. So you need to pick some starting node. Okay, and you are basically going to keep track of everything, all the edges that emanate from things that are already connected to that starting node. So you will um, add all the edges from that node to the priority queue. So PQ is priority queue. So you're going to add all of the edges from that node to the priority queue. And I should mention here that the priority queue should be lowest value is the highest priority. Okay, so a default priority queue, you usually pick the highest value. In this case, you want to pick the lowest. Okay, so you can add all of the edges from that node to the priority queue. Then you pull off an edge. If it's to an unvisited, so that's pulling an edge off of the priority queue. If it's to an unvisited node, um, then use that edge and add the new nodes edges to the priority queue. And if it's to a node that's already been visited, so you can keep an array of whether something has been visited or not. Okay, if it's to one that's already been visited, you just ignore that edge and you pull the next one off of the queue. Okay, so let's go back. I'll do the exact same graph that I had before, and we'll see how Prim's algorithm works. So A, B, C, D, E, F. All of those and put the weights in that I had before. Okay, so this is what we have, and we can keep track of it. We'll have some sort of visited array of A, B, C, D, E, F. Of course, you would use uh, numbered nodes instead of letters. I'm using letters here. So all of these will start out false. They will all say, no, it has not been visited. And then we're going to keep priority queue over here. And the priority queue will be lowest to highest values. So we have to pick a starting node. I'm just going to pick A as our initial starting node. So we pick A and we make this a 1. Okay, so erase that and I'll make that a 1. Okay, so we visited A, and we're going to put in all of the edges coming off of A into this priority queue. So in order, the lowest one will be 7, which is going to be the AE edge. And then we have 8, which is the AB edge. And we have 11, which is the AD edge. Okay, so we've got those 3 edges in the priority queue. We pull off the lowest one. So the lowest one that we have is the very first one, 7 from A to E. So we look at that one, 7 from A to E. It's connecting to a new node. Notice that E has not been visited yet. So we're going to go ahead and add E to our visited set. Okay, so we make that a 1 there. We are going to use this edge. That's one that actually gets used. I'll mark it right here in green. And then I have to add all of the edges. I add all of the edges from this to my priority queue. So these are going to be generally a little bit less. So we have one that is 1 that runs E to B. And we have one that is 3 running E to D. Okay, and we have one that is 9 from E to F. And we have one that is 10 from E to C. Okay, we don't have to add back in the E to A one because we've already used that. So we know that A was already visited. We can check and see. We don't even have to add them to the priority queue if we already know that it's visited. But later on, we might find ones that are. Okay, so again, we pull off the smallest one here. That is this one right up here, E to B. And so I check, and B has not been visited yet. So we're going to go ahead and add B in. We'll add that edge in. So 1, which is E to B. And we have to then add B's edges into the priority queue. Okay, so first one that we add, we don't necessarily know that it hasn't been added yet, but we would add another one from B to A, even though we already had AB in there. We don't know that it's in there. We would have, I'm going to move this 3 up. Should have left more space. Okay, because we are going to add 4 between B and D. We are going to add 5 between B and C. We're going to add 6 between B and F. Okay, and we will stop right there. Okay, so again, pulling off the smallest one at this point. Smallest one is 3 from E to D. So that will be this edge. D is again something new, so we can go ahead and add it in. So 3 ED comes out of there. But we've gone ahead and used it here. Okay, now we have to add D's edges in. So we have the 11 from D to A. We have the 4 from D to B. Um, Now, in both of these cases, we don't actually have to add those in. In fact, I'll just go ahead and take them out because we could check and we could say, oh, B is already marked true, A is already marked true. So we didn't actually have to add those in. We didn't have to add the earlier one in either, but I put it in to see how it could have come up. If you'd wanted to, it would all work. It would all still work the same. Again, pulling off the next highest one. So the next highest one is 4 from B to D. Okay, so we look, B and D have both been visited. So when we first put it in, maybe that didn't, we put in the edge from B to D. Now we've already connected to D. So B to D, this one we don't need to use. That is not going to be used in our minimum spanning tree because B and D are already connected. Next, we pull off the next one, which is B to C. That one will get used. C gets marked. This is 5 from B to C. Okay, so that gets pulled off. Oh, excuse me. We add C's edges in. We don't have to add back to B. We don't have to add back to E. We do have to add 2 from C to F. Okay, and then finally, last edge, we'll pull the top one off. It's actually the one that we just added in. So the 2 from C to F gets added in here. And that will mean that we have now visited F and we are done. And so we have a minimum spanning tree again. And we should look, if you look back here at the one up above, it's the exact same minimum spanning tree. So we generate the same tree either way. All right, so that's the basic idea of both Kruskal's and Prim's algorithms. Hopefully those are both things that you can implement. So there's reasons that you might want to use one or the other. So generally, if you have an edge list, then Kruskal's is easier. And if you have, uh, an adjacency list, okay, so this is where you keep, then usually Prim's is easier. Because otherwise, if if you don't have an edge list already, you don't want to have to visit every node and make your edge list. If you have an edge list, you don't want to necessarily have to make an adjacency list of everything first. Although very often, if it's a graph problem, you're going to need an adjacency list. Uh, so Kruskal's, if the only thing you have to do is a minimum spanning tree, Kruskal's is easier um, than one or the other. Again, running time, you can find cases where one or the other is going to is going to beat it. So there are some specific types of cases, some slight variations on minimum spanning tree that are useful to think about. So you could have a maximum spanning tree. And so this is one where you want to use Kruskals. That's the union find one. Uh, but where you order the whole thing max down to min. Okay, so you can just take Kruskal's algorithm, but reverse the ordering from maximum to minimum, and that'll give you a maximum spanning tree. So still a spanning tree, but you want to maximize the weight instead of minimize the weight. If you want to do a minimum forest, you can do Kruskal's until you need, or until you are at the number of trees that you want. Okay, so for instance, you might say, okay, I don't need to connect it into one single connected component. I'm okay to have three connected components. Well, in that case, you want to use Kruskal's algorithm because it's basically generating trees. And once you're down to three trees, you just stop there. So instead of n minus one for one component, you would have n minus three edges added for three components. Notice that Prim's algorithm is not going to work there because it's going to definitely connect from the first node, no matter what, and you don't really know which ones to remove afterward. Okay. I imagine you probably could like build the tree and then take some stuff away or some things like that, but you might as well just use Kruskals and stop earlier. Now there is kind of a there are some other ones you can have uh, minimum spanning subgraph. So some edges are already there. Okay, so imagine that you just need to connect some things and parts of them are already connected. So this one is easier to do. You can actually kind of do this with prims, but it's easier to do with Kruskal's algorithm. Um, you just add the already in edges first. It's possible to adapt Prim's algorithm to do this also. So where you say, oh, these links are already, like I'm already connecting nodes A and B and D and F. Like those might already be there, and then you just need to do a minimum spanning tree on what's left. You can do that with Prim's algorithm, but then you have to like find the already connected component and add all the edges for that component. You basically sort of you merge those nodes into a single node. It's a whole lot more work. Whereas Kruskal's algorithm, you just add those in and you work everything from there. Um, let's see. One other thing or two other things. We'll do the second best tree. So this is kind of interesting and obvious, but basically the what you want to do is the second best tree, it's going to be the minimum spanning tree, but one of the nodes is going to be different. But you don't necessarily know which one yet. Okay, so you will basically test what you get. Removing. And you have to test this for all edges. So, but for all edges. So what you're going to do here is you'll remove an edge and then complete the minimum spanning tree without that one edge. So you remove one edge that's in the minimum spanning tree, take that one out, and then see what you get. And so you're going to have to basically do n minus one minimum spanning tree operations because after you, or additional ones, because after you've found your MST, you have to go to each and every one of the edges, pull it out, and then try to find the solution from there. Then pull a different one out, find the solution from there, pull a different one out, and so on. So it ends up being actually pretty complicated. And then the last thing that I want to mention, and it's one of the ways that minimum spanning trees get used, is minimum spanning trees will often give you what we would refer to as minimax, which is minimizing the maximum edge weight. Okay, so if you wanted to find like if you wanted a path from say a path from A to B. Okay, so let's say that you had something like you're connecting cities and uh, you want to minimize the size of the gas tank that you need to be able to travel between a pair of cities. So you're not trying to minimize the distance. You might be willing to go through a very long distance, but you're trying to minimize the amount of fuel that you have to hold to get between any pair of cities. So you want to minimize the maximum length of the edges. So this is just going to be a subset of the MST. Um, gives the minimax path. Okay, so remember it's a tree, so there's only one path between two nodes. So you just take that path between the two nodes that you care about, and you can find whatever on the minimum spanning tree, and that's going to be the path that you have. Okay, so if you're given some general graph and what you care about is the minimax, you want to minimize the maximum, then you can do that by forming the MST and just traveling along the MST. Okay, so that's one of the maybe less obvious ways that MST gets used, but it does give you the same answer. So that's the summary of minimum spanning trees. Again, hopefully this was mostly a review for you, but maybe it gives you slightly different ways to think about it in context of some of the other things we've talked about. All right.